So 8.2?
Do you want us to turn in 8.1?
We will in a minute. Okay, so today we're going to talk about how we know if two triangles are similar. So we're going to begin with that. So I'll draw a couple triangles here for you. Okay, let's start. Similar or no? Everyone that's thinking, yeah, those are similar triangles? No. They kind of look like it, don't they? You know, if you were guessing, you know, you might say that. But is there anything in this picture that says those two triangles are similar? No. Okay? So you can't just say, oh, they look like it. Okay, we're going to go for it. That's not the way it works. We need something more. So let's if I can tell you that. Are they similar?
No.
Still no? Everyone agree? Okay. What if I tell you that?
Yes.
Now wait a minute. I hear a lot of yes, but are all three angles congruent? Yeah, that third angle theorem. Remember that one? If two angles of two triangles are congruent, then the third angles are congruent. So this is the angle similarity theorem. It's the only one you have to really learn. Remember when we were proving they were congruent triangles, we had side, 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 we had side, angle, side, we had angle, side, angle, we had angle, angle, side, and we had a hypotenuse leg, right? There were 5 different ways to do it. Well, with similar triangles, all we really have is this angle similarity theorem. And of course, if two angles are congruent, the third angles are congruent as well. So you just need to be looking at the pictures and make sure that, you know, it says they're similar. There's and maybe it has something like that in between them, or you have a couple of angles that match up. Then yeah, they would be similar. And I suppose there is another way we could determine if two triangles were in fact similar. You could have something like this. Are those two similar?
Not necessarily.
Nah, they're not similar. See, this 2, it could come out here more like that, and then this side could be out of proportion.
Teacher,
Okay.
could you excuse those students that are participating in the quiz bowl today? They need to go to the old CAD lab. Thank you.
What about now? All 3 sides are proportional, aren't they? They have that same scale factor. So as long as we have this 2-to-1 scale factor for all 3 sides, but you have to have all 3 sides. You can't just say one pair of sides or 2 pair of sides. It's got to be all 3. So let's be a little bit careful with that. You are going to see a bunch of different pictures where you have to determine if the 2 triangles are similar. And one of the ones we're going to see probably the most would be 2 triangles drawn together like this. A lot of times you may be given, let's see, maybe you're given this. Okay, so we have triangle ABC. We have triangle DBE. Are those 2 triangles similar? Do we have angle similarity? Are you seeing it? Everybody seeing it? So we got the one here, right? And then see the one they share in common? I mean, isn't angle B congruent to itself? Right? Okay, so it's congruent to itself. So they do in fact share 2 angles in common, so The angle-angle similarity theorem says that they are in fact similar. Let's see. How else can we show something like that? Those two are parallel. So is this little triangle on top and the big triangle? What do you think about that? Probably?
They are.
They are?
Because you can do it by the corresponding angles.
You think so? Yeah? So we've got parallel lines. Are these two alternate interior, alternate exterior? What are they?
They're
Corresponding. So they're going to be congruent, aren't they? And then do they share this angle up here again? Plus, aren't these two are also corresponding angles, aren't they? Okay, so in the picture, if it tells you two sides of the figure are parallel, is it usually just saying that just cause?
no.
Yeah, there's a reason they're telling you two lines are parallel, right? Because you have a transversal and you've got angles on there that you now know are congruent or supplementary or whatever we need them to be, right? So really pay close attention to that. How about those two? Similar? Maybe? Well, now, isn't that as good as we can do as maybe?
Well, yeah.
How about now?
Yeah, now they are.
Now they are. So we got angle-angle similarity? Because you have your vertical angles, right? So you always have the vertical angles that are congruent. So we do have angle-angle similarity. Similar? Yeah, good answer. That's one of the few times in the history of your schooling that is a fantastic answer. Isn't it? All right. How about now?
Yeah, now it is.
Kimball, how come?
Because of alternate.
Yeah, the alternate interior angles. This one and this one, right? They're congruent. Plus, don't we have our vertical angles congruent? And then these two here are alternate interior angles again, aren't they? Okay, so we have at least angle-angle. Okay. Writing a similarity statement. If I'm going to write a similarity statement, if I say triangle ABC is similar to triangle, which triangle is ABC similar to?
ABCD.
So E, D, then C?
Yeah.
So we have to name the angles in the corresponding angles, and ones that are congruent. So angle A and angle E, they're congruent, right? Angle B and angle D, are they congruent? And then, of course, angle C is congruent to angle C. Now, if I just give you, say, triangle XYZ is similar to triangle PQR, I'm giving you a lot in that statement. I'm telling you, those two angles. Mason, what do you know about angle X and angle P? They're congruent. Michael, what do you know about Y and Q? They're also congruent. Zach, what do you know about Z and R? Okay. Easton, what do you know about segment XY and segment PQ? Wait.
They're proportional.
Shh. You're not Easton, but good job. Yeah, they're in proportion. So angle or segment YZ and QR, they're going to have that. So if I said the measure of XY over the measure of PQ, it's going to equal the measure of YZ over the measure of QR. and that's going to equal the measure of xz over the measure of pr. So all of those are proportional. We good with that? So when you see these congruent statements, they're not there for nothing. Okay, there's something that we need to think about and help us. Okay. Now let's talk a little bit about why we care about similar triangles. Okay, so here's Mr. Collard standing here. Yay. Flagpole. Right? Now, sunshine. I'll make it red. Comes down, hits Mr. Collard in the noggin, goes down, hits the ground. Makes a shadow on the ground, doesn't it? Okay? Sunlight comes down, hits the top of the flagpole, comes down, creates a shadow on the ground where that flagpole, the shadow of it's on the ground. Now, I want you to think about these two triangles that I just formed right here. Okay? I'm assuming that I'm not drunk, so I'm standing straight up at a right angle to the ground, right? Usually that's how I am. What about this flagpole? Probably. That would probably be good, right? Even if it's not, though, I'll show you it works anyway. But what about the angle that this sun ray hits the ground right here and the angle that this one hits the ground at? Are they congruent?
Yeah.
Okay, so you got the sun, right? Got our sun. It's sending off rays of light in every imaginable direction, right? Every direction. Are all the sun rays from the sun parallel to one another? Are they, I mean, the Earth's the transversal here, and these two sun rays are coming along, and I'm saying, well, these are corresponding angles. I mean, that's basically what I'm saying, is that these two lines are parallel, but are all the sun rays parallel?
No, not really.
I'd say absolutely not. But are two rays that come from the sun, travel 93 million miles through space, and strike the ground a few yards apart parallel?
Yeah.
I'm going to go with yes. Now, you might be able to argue, I mean, one of these rays could have come from the very top of the sun. One of them could have come from the very bottom of the sun. That's a long way apart. Yet when they hit the Earth, for all intents and purposes, they're parallel. They're close enough. Sometimes you have to stop being a mathematician and start being an engineer. Close enough, right? So these two triangles are definitely similar triangles. Now I know I'm 6 feet tall, right? And it's easy to measure my shadow. I'll make it easy. My shadow's 5 feet. That's easy enough to measure how long your shadow is right there on the ground, right? What else can I measure that's easy here?
The shadow.
Yeah, the shadow that the flagpole is casting along the ground, right? So I know I can measure that and say it's 20 feet or something like that. So can we find the height of that flagpole?
Yep.
Well, sure. It's 4 times 6, isn't it? Right? Our scale factor's 24. Sorry, our scale factor's 4. We can also do it like this. We can say the height of the flagpole over my height equals the shadow of the flagpole over my shadow. Or we can say the height of the flagpole over its shadow equals my height over my shadow. They both work, don't they? Say we're consistent, like height over height equals shadow over shadow, or height over shadow equals height over shadow. As long as you're consistent, you're going to set up a true proportion, and you can solve that proportion. And of course, most of the time, it's not going to be 5 to 20, is it? No. Okay. And we're going to have to do a little bit of math. But that's what this is all about. It's a simple little process to be able to look at something like that. I mean, can that work on a building?
Yeah.
Can it work on anything? if we want to know how high anything is, it's a simple little thing to do, isn't it? Okay. Do you need any really special tools or rangefinders or laser levels or anything like that?
Yes, you need a tape measure.
A tape measure. Yeah. I don't even think I need a tape measure. I could just use a string and just say, well, from the tip of my finger to my elbow, I'll mark that off on the string and measure it in cubits or something. I can figure it out. I can figure out how tall that is. Okay. We did something similar. Speaking of similar, we talked about we have this creek, right? And we're standing on the edge of the creek, and we want to know how far it is across, right? And I had a hat on. Remember, this was an old one, and we turned our body so we were looking down the creek, and we just kind of put the brim of the hat so it was touching a rock across here like this, and then we turned back and looked across here, and we just kind of made sure that those two triangles were congruent. We actually formed congruent triangles when we did that, didn't we? That's a horrible picture. Do I need to put my hat on and demonstrate that one again? Remember that one? Yeah, I definitely do. So it was like, had my hat on, it turned like this, I put my hat down to the edge of the river, and then I just turn down the bank and I just kind of keep my head the same, and I find a rock that's exactly touching the brim of my hat, just like the river is, and then from me to that rock is the same as from me across the river. But do you see in that case, I'm not making two similar triangles, am I? I guess they're similar, but they're more than similar, aren't they? They're congruent, right? Okay, so this is a little bit of a different case. I hope that demonstration helped more than my crappy picture. Okay, easy lesson, easy peasy today. Here we go. Chapter 8.2.